In today's video, we're going to be looking at topic 1 of GCSE Physics, and that is the energy topic. Please make sure to pause and take notes where you can to make sure you're as prepared as possible for that GCSE exam. If there is anything in the video that you want explained a little bit further, comment it down below and I will do my best to answer you as quick as possible. But apart from that, I hope you enjoy and let's get to it. First of all, we have the different energy stores. So as you can see in the red box, there are 8 different energy stores that you need to remember for this topic. Kinetic, thermal, gravitational potential, elastic potential, chemical, electrostatic, magnetic and nuclear. Some are much more common than others, and the ones that you recognise are probably the ones that you need to know a bit more about. Most of you will know that there are equations linked to some of them, which we will get onto a bit later on in the video as well. There are 3 main different ways that energy can be transferred between these different stores. So as you can see at the top, I have an example of a tennis ball being dropped from a height onto the ground. Now at the top, the tennis ball is at rest, so it has no kinetic energy. All of the energy that it has is in its gravitational potential energy store. Now once you let go of that ball, gravity does work on it and pulls it down. Now in that time, the height is being decreased, so the gravitational potential energy decreases as the kinetic energy increases because it's speeding up. Once it reaches the bottom at a height of 0, just before it's about to hit the ground, all the energy that was in the tennis ball at the start has now been converted into the kinetic energy store. That is just one example. I would recommend you get familiar with plenty of examples and are able to explain the energy transfers going on there. Let's have a deeper look into kinetic energy. Here is the equation. 100% you should be familiar with this equation before going into your exam. E equals half mv squared. And as you can see underneath, I've written the word equation and the units that you should be familiar with as well. Gravitational potential energy, we have E equals mgh, or mass, times gravitational field strength times height. And again, the units below. Gravitational field strength can alternate between newtons per kilogram or meters per second squared. Be careful when talking about the units, depending on what the question involves normally. And then we have elastic potential energy, very, very similar to kinetic energy. And this relates to when things are being stretched or compressed. So for example, an elastic band is going to have a certain spring constant of the material, and then the extension depending on how far you stretch it. The spring constant changes depending on what material you're using. So everything will have a spring constant, but you can imagine something like an elastic band is going to be a bit easier to stretch than something like metal. So always bear that in mind, but you will never be expected to know the values. They will always give you the questions, and most of the time you'll just be substituting them in. Here we have specific heat capacity, a very important definition to remember. Specific heat capacity is the energy required to increase the temperature of 1 kilogram of a substance by 1 degree Celsius. And all substances have a different specific heat capacity, just like with the spring constants that we talked about a minute ago. There is also an equation. You are given this one in the equation sheet. The change in energy equals the mass times the specific heat capacity, which is denoted by a C, multiplied by the temperature change. The specific heat capacity does have some interesting units, so that might be a good one to remember. If you're ever unsure, you're actually able to rearrange the equation to get specific heat capacity on its own, and then from there you can work out the units depending on what equation you have. If you want me to make a separate video on that, please comment down below and I will do so. The conservation of energy, arguably the most important thing in all of the energy topic. Energy can never be created or destroyed, only transferred usefully, stored, or dissipated. Now, an interesting point about this is, using this theory, all the energy that we have in the world today is exactly the same amount of energy as we had when the world and the universe first began. We have just found ways to use it in more of an effective and efficient way. Power. So power is the rate of doing work. As the equation shows, anything that's to do with rate is often to do with time, because if something happens a lot quicker, you would say it's a quicker rate. You'll notice that energy or work done could be on top of this fraction, so take that into consideration when it comes to your exam questions. They could use work, they could use energy. Both mean the same thing, so don't worry about overcomplicating it. Next we have conduction and convection. This is all to do with how heat moves through matter. So conduction occurs in solids, and as you can see from the diagram, the particles, when they get hot, they vibrate, and that energy that they create from vibrating is transferred across the solid until all of them are vibrating, which makes the whole solid hot. Convection occurs in liquids and gases. So as you can see, I've tried to model more of a gas here. When all the particles are closer together, this is representing a hot area. And just like the fusion, all the particles spread out to fill that container, which makes the whole container hot. So just like when you're at home, you put the heating on or you have a fire on, the gas particles around the fire or from the heating source are going to be hot first, but then over time it heats the whole room or the whole house. Here we have efficiency and reducing unwanted energy transfers. A lot of these methods you will see from your house, so cavity wall insulation, loft insulation, draft excluders, and things like double glazed windows. You might also hear that things like carpets can help reduce this, but that's all kind of fairly common knowledge and things you can normally see in your house. On the other side, we have an efficiency equation. The efficiency equation looks a little bit more complicated, but if something is efficient, then the energy that you put into it will convert it into the thing you want out of it. So when you simplify it down into words, it can make a little bit more sense to you. Our total input is going to be the bottom of the fraction. And the thing that we're interested in is the useful output. So let's say you put 100 watts of power into a light bulb, but you only get 80 watts out of the light bulb of light. That means that 20 watts of that energy has gone to heating or maybe sound, but it just shows it's not going to be a fully efficient light bulb. And as that point at the bottom says, nothing is always 100% efficient and there is always something being dissipated within it. We're nearly at the end, but we have energy resources, so renewable and non-renewable. You should be very familiar with at least 4 of those on that list. If you can't name all 6, it's not the end of the world. If you can, amazing. And you should also have a rough idea of how they all work. So things like solar panels provide solar power. Wind turbines are for wind, believe it or not. Hydroelectric would be from things like dams. Biofuel is organic matter and animal waste and stuff like that. Tidal is from the tides. So geothermal often occurs from places that have a lot of volcanic activity, which produces a lot of naturally hot water. As you can see underneath, I've written pros and cons of both renewable and non-renewable. So renewable energy resources will never run out because we can renew them. They do less damage to the environment. They do still do some damage because obviously, for example, building a dam to provide hydroelectric power is going to disturb a lot of habitats and stuff like that. However, they can be unreliable. So for example, if you're in the UK, it's not as sunny as it would be somewhere else. So if it's not sunny, then you can't get any solar power from that. On the other side, we have non-renewable energy resources, things like fossil fuels, so you should be very confident with those 3. And also nuclear is quite a commonly forgotten non-renewable resource. And again, you've got the pros and cons on that side. Fairly similar to the renewable ones, just kind of the opposite. And finally, we have the national grid. So the national grid, I will let you read that stuff in the red box, will be very important. But as you can see on the diagram, the factory will produce this electricity, and then we use a step-up transformer to increase the voltage, which will basically make less resistance in the wires, so less energy is lost to heat as it travels through. It will go through the pylons, through the country, and then a step-down transformer is used, where it decreases the voltage again, and goes back to the houses where the power is at a safe amount to use within a home. And that is the end of the energy topic. The next topic I will make a video on for physics is going to be the electricity topic, so wait around for that one. But thank you very much for watching, and I hope that helped.